Hello, everyone. My name is Jae Kim, and I'm a PhD student at UNIST, South Korea. Today, I'm very happy to present our work, PPT, Patch Order Do Matters in Time Series Pretext Tasks at ICLR 2025. In this paper, we introduce a novel self-supervised pretext task for patch-based time series classification. The order of our presentation is as follows. We will first introduce why self-supervised learning is needed in time series, and then explain our methodological contributions and its corresponding experimental results. So, time series is very hard to interpret with the human's naked eye, distinguishing itself from other data domains such as images and natural languages. For instance, here is an image of a cat and also a music review in text. We can easily understand that just by looking at the explanation, the model is looking at the right features of the cats, such as the furs, to classify this image as a cat. For this music review, we can also understand that the sentiment here is very positive. But for time series, it's very hard to understand what is representing as in the raw data format. This is because time series lack semantics, which makes it hard to interpret as well. They exhibit strong temporal dependency and multi-channel characteristics. So, one of the biggest problems deriving from this non-interpretability is the hardship of collecting labeled time series data. We cannot rely on cheap crowdsourced labeling like we would do for images or text. As such, the labeling of time series usually requires a labeler to be present during data collection, or it requires an expert to annotate the time series. As such, while it is relatively easy to collect time series, it is hard to label them. Here, a natural solution is to leverage self-supervised learning. Self-supervised learning is the task of learning from unlabeled data, where the task is to enhance the generalization of model performance. So, how can you do this? This can be done by creating a pretext task. A pretext task is a synthetically designed or a pre-designed task that is made for a network to solve in a self-supervised manner. In light of this, our research focuses on answering the following questions. We first asked, how can you design a pretext task that leverages the temporal characteristics of the time series and models the interchannel relationships in time series? We also ask, can we leverage the recent patchwise methodology that is widely used in time series? So let me introduce our methodology. Our motivation for designing a novel pretext task for patch-based time series originates from two reasons. First, we observed that a large number of recent works have focused on representing time series with patches. Such examples include the SOTA models such as PatchTST and PITS, and even foundation models like TimeLLM. We also noticed that the predominant pretext task for time series is mask and reconstruction. However, mask and reconstruction does not explicitly model the temporal and channel relationships in time series, resulting in subpar model performance. So previous works to self-supervised learning can be mainly categorized into two. The first is mask-based approaches, where you would mask a portion of the time series and ask the model to predict what's behind the mask. Such examples include PatchTST, PITS, and VQMTM. Another approach is the contrastive approach, where we define similar instances in the representation space to be close, and dissimilar instance to be far apart. Such examples include TSTCC, CATCC, and TSGAC. Here, we propose our method called PPT for Patch Order Aware Pretext Task. We first provide an overview of our methodology. Here, our PPT is an order-aware pretext task for patch-based time series learning. We leverage the order characteristics in time series to provide self-supervision. Last but not least, we also introduce our novel metric called ACF costs, which can pre-assess whether a given time series dataset could benefit from our order-aware learning. Before we dive in, let me introduce a brief motivation for why we should leverage the order characteristics of time series. Here is a time series collected from a human activity recognition data. There are three different sensors that collect signals of an activity. When we segment the time series into patches, we observe that the pattern given at patch index 0 somehow can be repeated along the temporal axis. As such, we can presume that this repetitive order pattern occurring, which makes the time signal predictable along the temporal axis. Similarly, we can also observe such repetitive orderness along the channel axis. Here, we show that time series, these kind of natural order relationship occurs both in time and channel orders. We also outline the overall methodology of how PPT supervises this order information in time series. First, time series are represented as patches, and these patches are individually encoded into a latent representation vector using patch TST or PITs. These representations are then transformed to construct three different sets of patches: the original, the weak, and the strong. The first set is the unaltered original set, and the second set is the weakly permuted set, where patches within each channel are shuffled once or twice. So this weak representation will have a very close representation as the original patch representations. The last set is the strongly permuted set, where we shuffle the patches more frequently within each channel, making the order of patches close to random. After constructing these three sets of patches, we utilize them for consistency and contrastive learning. In consistency learning, we want to measure whether the order of the patch sequence is consistent or correct, in other terms. For this specific learning task, we utilize the original and strong permuted set of patches, where the learning is enforced in both time and channel dimension. Here, a binary cross-entropy loss is utilized to classify the original and strong sequences. The second type of learning is contrastive learning, where we place original and weak as positive pairs and also make the strong permuted sequences as negative pairs. As in the consistency learning, we utilize this contrastive learning in both time and channel order. So here is the detailed methodological section. So time series are individually represented into representation vectors using models such as patch TST and PITs. We construct three different patch permutations: the original, weak, and strong. In consistency learning, we perform time order and channel order consistency learning, where an autoregressive model is used to construct the context vector, and we employ binary cross-entropy loss to classify the original and strong sequences in both time and channel order. The contrastive terms are applied to make the original and weak closer in the representation space while making the strong far apart. As our method is a pretext task, our pretext task can be used individually as a self-supervised loss, and also it can be appended to the supervised term such as the cross entropy. However, as one might have assumed, not all time series will benefit from our order-aware learning. Certain time series tasks do not exhibit strong order permutation. As such, for those type of tasks, PPT would not greatly enhance model performance. To pre-assess such tasks, we propose a new metric called ACF cost, an autocorrelation function and cosine similarity. Here, an autocorrelation function is a function to measure whether there exists a strong periodical pattern within varying lags. Using this function, we calculate the autocorrelation function for the original and strong permuted set. We then measure their cosine similarity as noted in this equation. Our intuition is that when the cosine similarity between the autocorrelation function vector for original and strong is low, it means that the order information was not important. As such, there exists a strong order dependency. On the other hand, if the similarity is very high, despite shuffling the patches, it means that order was not essential for the task. As such, By using this metric, we can pre-identify whether a given time series task could benefit from our order-aware learning. This is the results section. Here we first evaluate our results on linear probing experiments, where we have applied our learning tasks on two different patch-based models, such as transformer-based patch TST and linear-based PITs. We observe that PPT enhances the performance of both models. We have also visualized the representation space of individual patches and colored them by the original patch indexes. We observe that with our learning task, the model is better aware of the ordering of patches, which also contributes to better model performance. We have also performed semi-supervised learning tasks where we first pre-train our model with unlabeled data and then fine-tune on limited labeled training data. Here, we show that on both 10% and 1% limited labeled scenario, our model obtains the strongest performance, especially for patch TST. We have also applied our learning tasks to supervised training. Here, we have three metrics where we observe that our PPT enhances model performance, while also learning better order information. We also show that the representation spaces are better constructed with our losses appended to the supervised training. We also visualize the attribution scores, where we show that using PPT leads to better identification of crucial inflection points in time series. We also performed several experiments to verify the positive correlation between the ACF cost scores and the performance gain obtained by our method. We show that ACF costs can successfully identify time series tasks which have strong order information and could potentially be benefited from our PPT learning. This is our conclusion, where PPT is an order-aware self-supervised method for time series, and here PPT is a plugin method for any patch-based time series model. We have shown that PPT had strong performances in especially tasks with strong order-aware dependencies. Thank you for listening to our presentation. If you have any questions, please feel free to email us. Thank you.